Welcome everyone for our talk on forecasting at Albertsons. My name is Diana Adam. I'm one of the data scientists leading the data science for merchandising and pricing at Albertsons. And
hey all, this is Amit. I'm part of the ML engineering team, and I help data science team make their models run.
First of all, a little bit about our company. Albertsons is a grocery chain with over 2,000 stores across the US. For those of you that maybe don't know about an Albertsons store in your neighborhood, you might shop at Safeway in Northern California or Jewel-Osco in Chicago, TomTom in Texas. We operate under about 20 brands throughout the US. Before we go into how we use serverless compute, I wanted to first touch on the business use case that we solved through this technical solution. So I assume most of you have been in a grocery store at least once, not necessarily Albertsons. So I wanted to go through an exercise of imagine yourself now in the grocery store. You go in and you look around and you see a lot of shelves with products, mostly grouped by category. You see pricing, you see some coupons. Maybe you pull up your Safeway app and you look for some personalized coupons that you can apply. And all of that you see around you is the result of a lot of strategic planning from our category managers. In order to do that, they need to be able to decide what products, how many brands, how much of that product, in which stores, for what time frame they have to sell, what pricing, what promotions, and they can't do that for the next day or the next week. They need to be able to plan ahead for the next 3 to 12 months. And for that, they need forecasts. And that's where we come in. This informs the granularity of our forecast. So we do forecasts of the category and geography and time horizon that they need. And that's what they use to plan ahead. However, they also need a way to make the best decision for the business from that perspective, from that strategic planning for their category. So they need something like a magic ball, where imagine that you have a magic ball where you ask a question, a strategy question, and then you get back very fast your forecasts that take into account that input from your strategy question. You're not happy with your answer, you ask again, get some other results until it makes business sense. So we have about 120,000 individual time series that we modeled, and through different types of models, we save those models in MLflow, and that's what's used to generate those forecasts. Now, for our magic ball, we need to be able to find the right models for our users' question. If they're asking about milk, we need to find those time series that refer to milk in Northern California. So we needed a way to find the right models from MLflow, give them the inputs, the new inputs, the strategy inputs that the user is asking for, and then rerun those forecasts very fast and provide the results. And that adds up to almost 1,400 concurrent time series that need to be rerun and serve. And that's where our ML engineering team came and used serverless computing to solve our problem. And I'll hand it over to Amit.
Thanks, Ed. So a quick summarization of the use case. We have a user where they want to test some business strategies and see how that would result in their ultimate forecast. Our user pretty much does it at different pockets of time during the day. So we needed something ad hoc. We need the model inference compute to come up in an ad hoc manner and in reasonable amount of time. On top of this, as Diana mentioned, user would actually consume the outputs from our ML model. They would digest them, see if they need to change their pricing strategies, and run the simulation again. For this to happen, they also needed something quick, preferably real time, if not near real time. With these two sort of considerations in mind, we actually did some industry analysis and found these two approaches, two extreme approaches that industry have been taking. One is the standard job cluster with batch inference. So a user would generate one of their strategies, they would hand over to us, we would kick off a job cluster, and that job cluster would load all the forecasting models, thousands of them, uses Spark for its batch inference. This works. Technically, this is a sound solution, but then we found on average, job cluster takes about 3 minutes to come up and to be inference ready. And the compute itself, the batch inference, takes about a couple of minutes. So this adds up to about 5 minutes to get just the model inference out of their strategies. This obviously wouldn't work for us, and we've seen other approach where some companies have been taking is they have handful of models, 5 or 10, and they would create REST endpoints for each model. And they would call these REST endpoints as and when they need. Again, works if you have fewer set of models in hand, but really doesn't scale for any use case in the order of hundreds or thousands of models. So we really couldn't take any of these approaches. For the first one, it's time, startup, latency, startup and inference. And second one, it's sheer hassle of maintaining thousands of endpoints. Imagine maintaining these thousands of endpoints, updating your model versions. You'd probably run out of your coffee pretty soon. So we were trying to solve multiple categories of problems here. One is the startup time. How do you reduce the cluster startup time in an ad hoc manner and get it up and running pretty fast? Second is the network latency. How do you call these thousands of models with reasonable amount of network calls? You don't want to be calling 1,000 network calls separately. You want them to be minimal and still get all the inference of your models. And the third category is pretty much the RAM size. Often microservices, whenever you deploy any microservice, RAM size is pretty small. And any request to increase the RAM size, probably your DevOps folks won't be too happy with it. So that's when we started to look for solutions for cluster startup time, we pretty much used Databricks Serverless compute. Think of serverless compute as your lightweight VM, so single VM, that comes up pretty fast. The smallest of the serverless compute comes up in about 2 seconds. It's inference ready in 2 seconds. And the largest comes up in about 30 seconds. So if you compare even 30 seconds with the 3 minutes that the job cluster takes, we are already looking at significant time savings. And serverless compute, neat thing about this is you can pretty much control when it should come up through code. So it also solved our ad hoc use case where our users hitting it at different points of time. You don't want your endpoints to be running 100%. So it has many advantages, serverless compute you can look up. The major ones being ad hoc nature. Configurable timeout, you can mention, hey, I want my compute to be 100% up. And you won't be charged for the total uptime, you would be charged for the time it's spent doing the model inference. So in long run, it's actually a little bit cheaper compared to running a Kubernetes microservice 100% of the time. We still had to host our models. So to be able to give these models to our user as an endpoint. Since we are in Databricks ecosystem, our standard choice was MLflow serving. So the combination of MLflow serving and the serverless compute sort of solved the cluster startup time. We were able to call it in an ad hoc way. It was good until then. So those of you who are not familiar with MLflow, MLflow is basically, think of it as a jar file for your models. All model dependencies could be inside a single MLflow model abstraction. So MLflow typically comes with flavors. Those of you are familiar, MLflow PyFunk, MLflow Prophet, TensorFlow. But the problem with flavors is it only lets you package one model at a time. It'll be something like this. So if you had your forecasting models as Prophet, each model will be a separate MLflow, each rectangle box is a separate MLflow model, and you would need to host them separately and call them individually to get your model inferences. This obviously doesn't solve any of the network latency that I spoke about, where we needed something like this. We needed to figure out a way to sort of package all of our or bunch of our forecasting models into one single MLflow abstraction so that we can serve them as MLflow endpoints. And that's where we found that MLflow PyFunk is a solution for us. So MLflow PyFunk really lets you package how many ever models you need, define your custom pre-processing, post-processing, custom inference logic. It's really flexible. And we ended up using MLflow PyFunk, group our models, deploy them as MLflow serving endpoints, and that helped us solve the network latency problem. The standard structure of MLflow PyFunk looks something like this. It comes with load context and predict being standard methods. Load context is typically a place where you load all your models. It could be from any storage database, could be from MLflow itself as a single flavored model. And you can play around with your artifacts once you loaded them. You can make them run faster with some techniques I'll talk about. You can reduce the model size once you loaded them. And the neat thing about this load context is it's not called every single time when you call the predict. It's only called the moment you create or the endpoint comes up, the serving endpoint comes up. This load context is called only once at that point. And every time you call predict, all your models are instantiated, packaged, and ready for inference. This helps you save a lot of latency in terms of prediction. So predict is a method where the actual prediction happens. As I said, you can customize, play around on how you want to do predictions of your model. Since we were exposing our models as endpoint, we had to take input features. And since it's an MLflow model, input features has to be a pandas data frame, because you cannot transfer a Spark data frame over network to do your inference. So the input for predict is a pandas data frame. It could have features for a single model, multiple models, and you can really decide how you want to do your inference. In our case, we played around with two approaches. One is, hey, start a process pool. Once you get a request for predict, start a process pool. Your pandas data frame has multiple models in it. Give each of these models to single processes and do inference in parallel. This was really fast. This helped us save a lot of latency, inference latency, but it's really not scalable. Imagine you make concurrent calls to this predict And in each concurrent call, you'd start a process flow. You'd soon run out of processes, and some concurrent request would add to a lot of latency because it'll be waiting for processes. So that's why we ended up doing standard for loop. We took a pandas data frame. It would have multiple models. We iterated through each model, picked the specific model which was instantiated in load context, and did our inference. While the predictions itself are sort of sequential, call to this predict is concurrent and asynchronous. Shall we talk about it? So we packaged our models, we used serverless compute, helped us solve two problems, but still the RAM size was a concern for us. Just for record, we had about 1,400 models. If you have profit as your forecasting model, often the case in many retailer use cases, profit has dictionaries. Python dictionaries are notorious for their RAM size. So we couldn't really use Python dictionaries, and we had to find a way to reduce the model size. And at the same time, our approach was pretty much come in post-training, because we valued the forecasting accuracy as much as the infrastructure optimization. So we didn't want it to touch the profit training and come in post that and try to reduce the model size. Very easy problem. So with profit, it comes with history attribute, which pretty much saves your entire training data as is. How many ever columns, how many ever rows, it saves most of it in the history attribute. So one approach we tried was, why don't we reduce the history and see if it reduces the RAM size? It did quite drastically. For some numbers, we went from 1.2 gigs to 120 MB, saving about 30% of original history. Quite a lot. But actually, it had a drastic impact on model forecasting outputs. So we ended up not taking profits history. I know there are some implementations which can replicate profit with some linear models, like linear regression with some regularization. It comes close to profit, still not exactly profit. So we didn't really take that approach either. So we resorted to some very simple techniques to reduce model size. It actually helped us quite a lot. So this chart talks about that. Instead of loading profit dictionaries as is, we converted dictionaries to pickle. That saved some size reduced some of the model size. From pickle, we reduced it further with standard compression techniques, nothing fancy. LZMA, GZIP, these are the ones. So if our pickle was about 3 megabytes, compressing it through LZMA brought it down to 28K bytes. So this was about 99% saving on our RAM size. So if you had other forecasting models, anything that is weight-based, you could do a process called quantization. Some folks might have neural networks for their forecasting, that's why they could use quantization. Just for reference, one model weight in floating point 32 occupies about 4 bytes on your RAM. If you convert that to floating point 16, it goes down to 2 bytes on your RAM. So you could say 50% of your model size for one weight. Obviously, you'll have tons of model weight parameters. You can reduce quite a lot if you do quantization, which essentially changes data types of your weights. All right, so combining all of these pieces together, first was our training pipeline, train our models, different granularity, and it's normal that once you train sort of potentially thousands of models, you need to persist them somewhere. And it's normal for people to write them to storage instead of MLflow. You don't want to be creating 1,000 runs under an MLflow experiment. So it's normal that people write it to some storage, Snowflake table, blob, etc. And we sort of combined all of our solutions into a small Python framework, wherein we packaged models to MLflow, PyFunk. We reduced the model size while we were doing it. and we created endpoints with serverless compute. It's pretty much the next steps. So all these pieces can be part or can be attached to your training pipeline. They can run on the same cadence. And when we created our ML flow models, we actually registered in UC. UC is again a very neat option. The so-called cascading rollout of new model versions without bringing an endpoint down. UC helps you achieve that. So we persisted our models in UC. So once we had this pipeline, the way user interacts with it, they have certain rules, as I said, some strategies. And they would actually be intercepted by small REST API that we built. This is the general purpose REST API. This is not, this is needed actually because the ML for serving endpoints, those are for inference only. Those endpoints are for model inference, not for regular exception handling, routing, and stuff. So we intercepted user requests with the regular REST API. That REST API knows how to translate user strategies into what models are required to do the forecast. What are the model identifiers that are needed to be forecasted? And obviously, what are the features for those models? And we used a small inference helper to distribute these requests to serverless compute. So you can't send all 1400 models in a single request. You need to potentially divide your pandas data frame into multiple chunks, send each chunk as a separate request to your endpoint. We used a small helper to achieve that. Double clicking on the what goes exactly into our framework. These are the first two steps that you've already seen. The first step that happens inside our framework is obviously loading models from wherever they are. Then packaging them through MLflow PyFunc. This step is what we call as artifact management. Essentially, serialize them to make them run faster, compress them to make them lighter. This is the model artifact management step that we did. And we registered it to Unity catalog registry. And we created serving endpoints. All through code. So far I've spoken about architecture, and I want to deep dive into some comprehensive examples, like how do you send, what should be your pandas data frame like, how do you compress the models, etc. Here I'm talking about a small example where you send in a single request and you have multiple models inside your pandas data frame to be forecasted upon. Since it's a time series forecasting use case, you would have multiple rows, and all those multiple rows would potentially count as a single observation, where each row is a feature which is in a point in time. So you have all your feature columns, and you needed to have some model identifier, not in any order, but to just mention that this specific row needs to be combined and put in this model's file to do the. So for that grouping to happen, you need to have a model identifier, you need to have your feature column. And this has to be the pandas data frame. So once the data frame is created, you can convert that to a dictionary. Pandas data frame, convert it to a dictionary, put it inside JSON payload, and use Python's request package. Standard REST request, no distribution yet. You can hit the serverless endpoint and get the response. So the actual sort of distribution happens something like this. On the far left, let me see if I can draw something. Yeah. So on the far left, this is your original pandas data frame. It could have 1,000 models, 1,400 in our case. There were 1,400 model identifiers. So this column of model key has 1,400 unique values. And we had about 52 rows per model. 1,400 times 52 was the size of our pandas data frame. So if you have a data frame like that, pay attention to this block, pretty much splitting that data frame into chunks. This is what I've spoken about. And we consider each chunk technically as a REST request. One chunk could have 10 models, another chunk could have 20. You can play around with the numbers. So we essentially chunk the input pandas data frame into how many models it has based on the model key column. We consider that a REST request, and through our helper, we send the REST request to serverless endpoint. You could imagine if we had like 1400 models, there will be multiple chunks. Even if you mention 50 per chunk, there will be multiple chunks. And that's where the concurrency part comes in. We call each of these chunks in concurrency. Wherein inside each request, if you recollect the predict method, it's a for loop, but it's happening concurrently. It would do all those inferences, and our helper collects all the different chunks as forecasting output, aggregates them, and sends the result back to you. So stepping into some code, as I mentioned, we could do all of this through code. Databricks serving is the class. You could say, what is the URL that you need as a suffix? Typically, it comes with the workspace URL will be the prefix. You can mention any suffixes you need. And you could say, what is the size of your compute? As I've mentioned, largest is 30 seconds, smallest is a couple of seconds. You could mention where your model is, endpoint, version, etc. One more neat thing about the Databricks serving class, it lets you define permissions at a very fine grain. You don't want all your business users to be continuously simulating. You could say who can just query it for inference, who can just view the endpoint metadata, and who can update and delete the endpoint. All of these you can mention while you're creating. And this is a small snippet of our inference helper, wherein we've mentioned, take my data frame, batch size is how many models per REST request, number of concurrent requests, 4, 32, 64. And some applications which are latency intensive as ours do not prefer any delay between concurrent requests. I'm sure those who are familiar with REST API would know. So I'd suggest if your latency is critical, don't mention any concurrency, any delay between concurrent requests. And if you mention the endpoint, you can use async.io to do all your requests concurrently. Okay. Don't want to keep you waiting to some latency numbers. So our benchmark was job cluster with batch inference. 1400 models, 52 rows per model. It took 5 minutes. That's 350 seconds. Now, when we used all of our solutions, serverless compute, MLflow PyFunk, and the compression, we hit the endpoints with 10 models per request. And we had the standard 32 concurrency, which resulted in 140 requests in total. So that took us about 48 seconds. And this is the very first time when we hit the serverless endpoint. The same request, 10 models per request, 32 concurrency, 52 rows. It's 20 seconds when you hit the second time, because the first time is the warm-up time. Our best results came with 30 models per request. Same configuration, pretty much everything after that, it's about 14 seconds. So comparing 350 seconds to 40 seconds, you're able to save in region of 90 to 95% for the inference latency. And it's almost at the same cost as a job cluster would. So this is really neat. And the way we built our framework is pretty much extensible to other models as well. It doesn't have to be Prophet. You can do this with all other models. Model loader pretty much doesn't depend on Prophet. Package to MLflow PyFunk, not dependent on models. And artifact management, this is where you serialize and compress your models. You could use Onyx to serialize if it's other models. Onyx is essentially changing the very layers of your model. If you have, the classic example is if you have a convolution layer, Onyx will change it to a bunch of batch normalization layers, and which essentially saves you inference time. And then you would export your models, register them in UC, and create it. So it's really extensible to other model types as well. With that, I'd like to take this opportunity to thank our engineering team, our data science partners for giving us a cool problem to solve, and our product team.